Alright, in this video, we're going to go over the basics of Amperes Law. And before we get into it, I should mention one thing. I'm guessing the point where you've reached in your class is you've only considered this term. This was a term that was added in to Amperes Law. It's called Maxwell's correction. And I'm guessing you guys have not dealt with it yet, so we're just going to consider this part of Amperes Law. Alright, so Amperes Law states that the integral of the magnetic field in a closed loop, you see that all right? The integral of the magnetic field in a closed loop is equal to mu naught times the current enclosed in that loop. Now, what do I mean by this? Let's say I had a magnetic field looking like this. I had a closed path looking like this. And again, we're going to integrate in the counterclockwise direction. That means if current is coming out of the board, it is considered to be positive. If current is flowing into the board, it's considered to be negative. So if I have some current that's coming out and some current that's going in, and I have a mixture of these, right? I have all of these currents coming out of the board, into the board. If I add them all up, right, and we let the negatives cancel the positives out, right? So if I have, 1 ampere coming out, 1 ampere going in, the net is 1 ampere coming out. The net current enclosed, multiplied by this special constant, is equal to B dot dl integrated over this path in a counterclockwise fashion. So, with that, we can jump straight to the most basic example of Amperes Law. And let's say I had a single wire carrying current out of the board. Right? So the current's flowing like this. I want you to find me the magnetic field strength and direction at a point, some distance r from the wire. Well, let's choose a circle of radius r. Oh my goodness. A circle of radius r as our integral. What's that going to mean? Well, at the same distance away from the wire, the magnetic field should have the same value. And it's always going to circulate around the wire like this. So, when we carry through this calculation, say it's the left-hand side of Amperes Law, right? Since the magnetic field has the same direction and magnitude everywhere, it's always going to be directly along the path and not perpendicular to the path. And it's always going to have the same magnitude. This is just going to become B times the length of this path, which is just the circumference of the circle. B times 2 pi r. I should write that better. B times 2 pi r. And then what is the current enclosed? Well, let's just call it I. Equals mu naught I. So then this gives the easy derivation for magnetic field along a straight wire. B equals mu naught I over 2 pi r. So now, let's do a different version of it. Now instead of a wire, let's say we're looking now inside the wire. So we still got all this current coming out at us, and I won't draw them all because, and I want to find the magnetic field at some distance from the center of the wire, some distance r, right? And it's got a current density. This is current per unit area, and it's usually denoted with J, or capital J. It's usually denoted with J. So let's say this entire thing has radius big R, and this is radius little r. And we want to find the magnetic field strength here, on little r. Alright, well, the total amount of enclosed current, again we'll take it as coming out of the board, is going to be J times pi little r squared. And then, again, we can use symmetry because the magnetic field should have the same strength here as it does here, as it does here, here, everywhere along the circle. And it should also have the same direction. And it should always be directly parallel with whatever segment of the circle we're looking at. So this dot product always ends up being just the magnitude of B, which is the same everywhere. So this is just B times 2 pi r. So then we just equate these two terms. B times 2 pi r equals B times 2 pi r equals mu naught J times pi r squared. Divide both sides by 2 pi r, and we solve for B, which is going to be mu naught J r over 2. There we go. Last example. Now let's consider a hollow cylindrical wire. So, draw that a little better. So the idea is that there is nothing, the current is only flowing through here. There's no current on the inside portion of this. I want you to solve for the magnetic field right there. And again, we're going to pick a circular path of constant radius r. But notice this time, right? So we can B times 2 pi r is equal to, what's the enclosed current inside this? It's 0. So it's mu naught times 0. This then means B is 0. So even though we have all this charge, all this current flowing around this region, the magnetic field inside of it is actually 0. Calculations involving Amperes Law, basically what you want to do is exploit some kind of symmetry, like how we realized that the magnetic field should have the same strength everywhere along this path, should always be parallel to the path, and so we can always simplify that path integral into this. Yeah.